Hi, in the last lecture, we have seen the way of using machine learning algorithm to make prediction on house prices. We have used linear regression by least square method. Today's topic is another way of doing linear regression, that is gradient descent. We know that when it comes to linear regression, we want to fit our data to a line. The equation of a line is y is equals to mx plus c. Now, how to reach to the best or optimum combination of m and c? Well, we can do it by performing the least square method as we have seen in the previous lecture. Now we can do the same thing by performing iterations, meaning that we start with a guess and then see if our guess makes sense, and then try to make a better guess and so on until we find a very good combination of M and C. Imagine standing on a mountain blindfolded and we want to come down to the lowest point. What do? We start by making a guess, we take a step, we feel whether we're going into the right direction, we set a pace of or speed and proceed, we take the next step and repeat until we reach the valley. Trying to find the local minimum for a function through iteration in this way is called gradient descent. There we go, you have the formal definition of gradient descent. Now in gradient descent, as I have mentioned, similar thing happens, similar to descending from the peak of a mountain to the lowest point. Basically, we try to find the local minima or the minimum value of a function. First, we take a guess for M and C, and we set a speed. In math language, it's called learning rate, the speed. Now, we have to learn just one terminology, that is cost function. Remember, in the previous method, we try to lower the sum of square of errors. In gradient descent, we do similar thing, just in a different way. When we have a set of data and we plot it, there is a difference between the actual data and predicted data, right? And let's call it an error. Cost function is the sum of square of error, and we want to minimize the cost function, meaning we want to minimize the error. Why do we need this cost function? Well, to gradually minimize the cost function means to gradually reducing the error, meaning getting close to the actual data. In other words, making a better prediction. Okay, that's step one, defining the step function. Now, step one is to define the cost function. Step two, we assume just a bit of knowledge on partial derivatives. You can just make a quick Google search to make yourself familiarized with it. We're going to skip the detailed steps as this is available everywhere. We'll assume that we know the result just to save some time. First, step two. Here we do two different calculations. Once we calculate the partial derivative of the cost function with respect to M, and then we calculate the partial derivative of the cost function with respect to C. We get two expressions like this. Don't worry, you don't have to do the steps, but if you're interested, feel free to do it or go through some online resources where the steps are done. Now, what do we do with these expressions? Before going into that, let's talk about the learning rate. What about the learning rate? We set a reasonable value for it. If we set a very high value, it will overshoot the minimum, and we may not reach the minimum ever. And if we set a very low value, we have to proceed very slowly. So we need an optimum value. For most simple linear regression problems, value of learning rate is 0.1 or 0.001. This kind of values will work. So what have we done so far? We've started with an initial combination of M and C and a learning rate. We have calculated the partial derivatives of the cost function with respect to M and with respect to C, and end up with these two expressions. And what do we do with it? What do we do with these expressions? We update the values of M and C by using these expressions. Okay, we replace the old values of M with the new values. That is the new value of M is equal to old value of F minus L times dm. That is the first expression. And the new value of C is the old value of C minus learning rate times derivative of C. That is the second expression. So that's how we use these two expressions to get the updated values of M and C so that we can proceed towards the optimum combination of M and C that will give us the least error. And what do we do after we get the updated value? We run it through a loop. That is, we run some iterations. Let's say we do the same thing. That is, we update the values of M and C for several times, several iterations, let's say for 10 or 100 iterations to reach the optimum combination of M and C. And it means in coding, we have to run a for loop perhaps for 100 times, meaning that we try to find the best combination of M and C 100 times. What do we end up with? We print them. And after running the loop, we get a combination of M and C, which is the perfect combinations that we were looking for. So is it a good prediction? Let's find out by going through the coding. We have this data set. As it's a linear regression with single variable, we just have two columns, one independent, one dependent, that is X column and Y column. The data looks like this. It's called gd.csv. And the first part of the coding is the same. We set the directory, we import the libraries, although we haven't used it in the gradient descent. But this is kind of a format that would be very convenient for us for starting to write any code. And we import the dataset gd.csv, and we call X as the X column as X, Y column as Y, and we visualize the data frame. Okay. So actually we're using pandas here to read the CSV files. And then we get into the gradient descent. What did we say that we have to start with some initial values? We have to set the initial value of M and C. Let's say they're 0. And we have set a learning rate, how fast we want to approach the optimum combination of M and C. And we run 1,000 iterations. A for loop for I in range iter, that is for 1,000 times, our predicted value is equal to mx plus c, which we already know. And then we set the dm value as the expression we have got. We set the dc value as the expression that we have got previously in the theory. Remember that dm is this and dc is this. We just need the n and y pred. And then we update the m values, m minus learning rate times dm. C, updated C is old C minus learning rate times dc, as we have seen in these expressions. And we just, at the end, we print m and c, so we get the slope and the intercept. And we can actually test them, how well they work. Probably it will not be able to predict it very well. Perhaps there will be some error even after running the gradient descent. So we can take, let's say, the first X value to test it. Let's say 48. For 48, the actual value is 60. Let's say how the gradient descent predicts it. I have set an X value for 48, and I have used the M and C values to predict Y is equals to mx plus C. You can see that Y is 71. The actual value is 60. Where is it? Yes. The actual value is 60, but it has predicted 71. So not that good prediction, but so what can we do if this is not a very good prediction? Definitely we can run some more iterations, or we can try with different combinations of iteration numbers and learning rate. We can increase or decrease the learning rate to get the optimum learning rate for this particular set of data. So that's the typical troubleshooting that we do for this kind of linear regression to make a good prediction. So that's how we do linear regression. We do gradient descent to make a prediction on this kind of data set. And hope you have found the tutorial on gradient descent helpful. So far, we have seen how to use machine learning algorithm to do linear regression with single variable. Next, in the next lecture, we will learn the next topic, linear regression with multiple variables. Till then, enjoy machine learning, and hopefully we'll see you in the next lecture. Thanks.